Okay, so let's take a look at a few exit problems now, and these are actually the exit problems 6 through 9 in the exit problem document that I sent you in the last announcement. So go back to the 5.1 announcement and pull up those exit problems, and you'll see 6 through 9 in those exit problems are exactly what I'm going to go through right now. So this very first one says use sigma notation to write the sum. And so we can see the pattern. It's 3 over 1 plus 1, 1 plus 2, 1 plus 3, up to 1 plus 10. And so when I write this in sigma notation, I would say, okay, my rule is 3 over, that would be 1 plus some index I, and that index is what's changing. And I can see that the lower bound for that index is 1, and then it's going all the way up to 10. And so I would write this as 3 over 1 plus I as I goes from 1 to 10. In terms of the multiple choice, that ends up being A, and I guess they didn't use I, they used J instead of I, but remember that variable is completely arbitrary. You can use whatever variable you want. Number 7, this is actually a really tricky question. It says use the properties of summation in theorem 4.2 to evaluate the sum. And so before we do that, remember that those properties that we looked at before, like when we saw, for instance, the sum of I was equal to n times n plus 1 over 2, it was very specifically based upon the fact that I was going from 1 to n. And in this problem, we're going from 3 to 28. And so what I recommend for a question like this is let's actually go through and work with it as if it was I going from 1 to 28, and then we have to subtract off what essentially would be the first term, which is what you would get by plugging 1 in for I, and then you also have to subtract off the second term. And so you could do the sum of 3i minus 4 from 1 to 28, and then take off a1 and a2, and that's going to give you the same thing that you would get if you do it from 3 to 28. And again, the reason it's helpful to do this is because when we break this up right now and use these properties of sums, those properties of sums were based upon I going from 1 to n. So I would break this one up and say this is the sum of 3i as I goes from 1 to 28 minus the sum of 4 as I goes from 1 to 28. And the 3 can come out in front. Remember, it's kind of like that constant multiple rule idea. So you have 3 times the sum of I, and the sum of I is n times n plus 1 divided by 2. It's exactly what I have right here, but my n is 28. So when I pull the 3 out in front, I have the sum of I. So that's, since I is going from 1 to 28, that would be 28 times 29 divided by 2. And then we have minus, this is a constant, and we're summing that 28 times. And so minus 28 times 4, or that constant times n. And so, so when I plug this in, I get 3 times 28 times 29 divided by 2 minus 28 times 4. And that gives me 1,106, but that's not my answer. So we're going to have to take this, and we still have to subtract off A1 and A2. So far from this piece, I've got 1,106. That's what we just saw. And now we are going to subtract off what we would get if we plugged 1 in to this to get our A1. So if you plugged 1 in, you'd be subtracting off 3 minus 4. So you would be subtracting off a negative 1. And we're also going to subtract off my A2. If you plug 2 in, you're going to get 6 minus 4, which is 2. So this actually gives us 1106 plus 1 minus 2. So 1106 minus 1, or 1,105. So our final answer is 1,105. And I think that the best way to approach this question was ignore that it's going from 3 to 28 and just pretend it's 1 to 28, and then just say, okay, well, if you are incorporating that first and that second term too also, when I was 1 and I was 2, we got to make sure we take those back off at the end. Okay, and this is another one where even though you're using these properties of summations, you can plug this into your calculator. Remember how we did that before, where we did the sum of the sequence, and we put this expression in, comma x, comma 3, comma 28, and you would get that answer immediately. And the nice thing is right now I'm not going to be there, harping on you to use these properties. If you want to use that tool in the calculator, you're more than welcome to it. Of course, I think it's always good just to at least know where all of this stuff comes from, and ultimately your calculator has a lot of those formulas programmed into it. Okay, number 8. Number 8, we've got a lower and upper sum that we're computing, and in this problem we've got 4 subintervals, so the picture is all set up for us, and we just need to find these areas. And so, like I mentioned in the last video, when you get these questions, please don't use the complex area formula. I know that all of you are capable of doing base times height 4 different times, so I strongly suggest doing that. So in this case, if this is going from 0 to 1, let's do the lower sum first. If we're going from 0 to 1, then this would be, or the length of each base is going to be a quarter, 0.25. And so in our lower sum, we would have 0.25 as our base, but then our height of that first rectangle appears to be 1, and that's what you would get if you plugged 0 in for x into this. Because notice the height of that first rectangle, your curve starts off like this. So the height of that first rectangle is based upon the lowest y value on that interval. That's based upon an x value of 0. If you plug 0 into the function, you get a y value of 1. So the first rectangle has an area of 0.25 multiplied by 1. The next rectangle has an area of 0.25 multiplied by, it's not 1. What's this x value here that's getting plugged into that function? That x value right there is 1/4. So it's going to be, the height is going to be the root of 1/4, or the root of 0.25 plus 1, because f of any x value is the root of that x value plus 1. So if our x value is 0.25 or 1/4, that's how I would set that up. The third rectangle, again the base right there, 0.25. The height of that third rectangle, you can see it's right here, it's based upon an x value of, that would have been 2/4 or 1/2. So the y value, when x is 1/2, is the root of that x value, the root of 1/2 plus 1. And then the last one, 0.25 times, looks like the height there would have been f of 3/4, so you'd have the root of 3/4 and then plus 1. So in my calculator, it's going to look like this. It's going to be 0.25, here, let me click on that, 0.25 multiplied by 1 plus 0.25 multiplied by the square root of 1/4. Make sure to close those parentheses off. Do I want to close those parentheses off? This is what I'm going to do. Let's do this. Let's delete that. And I'm going to get out of that square root. So 0.25 times the root of 1/4 plus 1. So you see how I want to make sure that square root did not go over everything, because the square root is not over the plus 1 there. Then we have 0.25 times the square root of 1/2. Then get out of that square root, plus 1. And then the last one, 0.25 times the square root of 3/4. Again, get out of that square root, plus 1. Whoops, it looks like I forgot my parentheses in this one. So let's go back. I'm going to insert my parentheses and then evaluate, and we should be good now. And we get an answer of 0.8765. Okay, and what did I do wrong here? So I've got 0.25 times 1 plus 0.25 times the root of 1/4. Oh, I see what I did. So let's go, I'm going to go back and just correct this real quick. I pressed second enter to pull my entry back up. Did you see that I missed a plus sign in between a couple of these values? So I need to have a plus symbol right in there. So let's go back to right here and let's insert a plus sign. And now I press enter. That is more like it. So when I set this up, I should get a value of 1.518 for my lower bound. And you can see just based upon those answers that our answer is going to be B. I think it's great practice if you were to just do base times height 4 times with your other rectangles. And you can see that when you go to the upper bound, that a few of your rectangles are going to be the exact same. You're actually going to have this rectangle again, you're going to have this rectangle again, you're going to have this rectangle again. So you would probably want to subtract this one off and then add that new big one in. But that would be the quick way of arriving at your upper, or just do base times height 4 times. And you should be able to get 1.768. And then in this last one, number 9, we're just doing a limit as n goes to infinity. And so the nice thing with this is we know the rules for limits at infinity, and they don't require us to know what the entire numerator and denominators are, as they're, if we were to simplify them all out. What we rely on is the leading term in the numerator and denominator. And so we can see that this numerator would be n times 2n. So your numerator would be a 2n cubed, and then there'd be a whole bunch of other stuff. But your denominator is 3n cubed. And so if your numerator is 2n cubed, as its term with the highest power, and 3n cubed in the denominator, then we know that we can apply the rules for horizontal asymptotes, and it says when the degree is the same in the numerator and denominator, take the ratio of those coefficients, and our answer in this case would just be D, which is 2/3. So hopefully these practice problems help. Like I said, I think this is probably one of the biggest ideas in this unit, in this section, being able to approximate areas just through lower bounds and upper bounds and things like that. You've also seen some of the more challenging work that goes into finding an exact area, and and you got to look out for some shortcuts like what we saw in number 7. But for the most part, I think that this should give you guys a good foundation to jump into the homework now. So let me know if you have any questions.